This is a new topic of FFT or fast Fourier transform. Let me tell you, this is not another or a new method of transformation or Fourier transform, but it is a faster method by which we can solve DFT. Here we are trying to solve the previously learned process of Fourier transform, that is discrete Fourier transform, in a faster way, or we can say FFT is an algorithm which helps in computation of DFT. As mentioned before, it is a numerically efficient method to calculate DFT. It is an algorithm which was first designed by Gauss in the year 1805, but he didn't get much of recognition, and which later was coined by Cooley and Tukey in the year 1965. As described earlier, the equation of DFT is x of k is equal to summation n going from 0 to capital N minus 1 x of n e to the power minus j twice pi by n capital N into kn, where again k goes from 0 to n minus 1. Here we will see that we need capital N complex multiplications and capital N minus 1 complex addition for finding each value of xk. That means we have n square number of computations for direct DFT. If we solve DFT with the help of formula, we have to perform computations in the order of n square, neglecting the other constant terms. We have something computation which will be in the order of n square. But if we follow FFT, the number of computation will be in the order of n log base 2 capital N. Now, it can feel like n square and n log base 2n doesn't have much of a difference, but the difference will come into existence or will be a matter of consideration or will make a huge difference when we have capital N of higher value. When the value of n increases, the difference between the two ways of solving DFT becomes very important. Now here, if a table is shown where if n is 1000, n square is 10 to the power 6 and n log 2 base 2n will be 10 to the power 4. So there is only a difference of 100. But as we go on increasing 10, we see that the difference between n square and n log n is getting bigger. When n is 10 to the power n, n square becomes 10 to the power 18 and n log base 2n becomes 30 into 10 to the power 9. So herein we see a huge difference. Let us consider that for each computation 1 nanosecond is required. So for 10 to the power 18 computation we will need 10 to the power 18 nanosecond, and for 30 into 10 to the power 9 computations we will need 30 into 10 to the power 9 nanosecond. Now 10 to the power 18 nanosecond is approximately 31.2 years, whereas 30 into 10 to the power 9 nanosecond is approximately 30 seconds. The difference is quite visible when n increases or n is a higher number. Now, FFT exploits some of the properties of the Twiddle factor Wn. As already mentioned, W suffix capital N is e to the power minus j twice pi by capital N. Now, it has two properties which we will exploit in solving, or which comes handy in order to derive the algorithm of FFT. The first property is complex conjugate symmetry. Here, Wn to the power k multiplied by capital N minus n would be equal to Wn to the power minus kn. Now, Wn to the power k of n minus n can be written as Wn kn into Wn minus of kn. Now, Wn to the power k of capital N can be written as e to the power minus j twice pi by capital N into k into capital N. Capital N gets cancelled. What we are left with is e to the power minus j twice pi k. Now, its value is equal to 1. So, we are left with Wn to the power minus kn, which can be written as Wn to the power kn whole to the power star, that is complex conjugate of Wn, kn. Now, periodicity in n, k. Wn kn, as already mentioned, is periodic with respect to n and k. Wn kn can be written as Wn to the power k into capital N plus n, or Wn to the power k plus n into small n. If we expand it and put it in terms of e to the power minus j twice pi by n, we will see that this periodicity property holds true. Now, among the many algorithms for FFT, in our scope, we will study two algorithms. The number one is decimation in time, and the number two is decimation in frequency. It is built on the concept of breaking big DFTs into smaller ones. And here we have to assume n is equal to 2 to the power m always. In this algorithm, we have to take n is equal to capital N is equal to 2 to the power m. M can be any integer. Now, what we do is we break the DFT equation into odd and even parts. We separate the summation by taking even parts of xn together and odd parts of xn in a different summation. Now, if n is equal to twice r, it will guarantee that x of n is always a even number, where r is equal to 0, 1 up to n by 2 minus 1. Similarly, if n is equal to twice r plus 1, it will guarantee xn to be an odd number. Now, what we do is we replace n by twice r for the even part and replace n by twice r plus 1 for the odd part. And summation also gets changed from r is equal to 0 to n by 2 minus 1 and r is equal to 0 to n by 2 minus 1 for both the cases. Now, if we solve it, the first term can be written as summation r is equal to 0 to n by 2 minus 1 x of twice r wk to the power 2 whole to the power k r. and w, and the second part becomes wn to the power k, because if we break wn to the power twice r plus 1 into k as wn twice r into k into wn k, we bring out wn k, and because it is independent of r, and within the summation we write r going from 0 to n by 2 minus 1 x of twice r plus 1 wn to the power 2 into kr. Now if we notice, wn to the power 2 is equal to e to the power minus j twice pi by capital N into 2, which can be also written as e to the power minus j twice pi by n by 2. That is, it can be written as wn by 2 if you compare it with the Tudor factor wn. Instead of e to the power minus j twice pi by n, we have e to the power minus j twice pi by n by 2. So we write it as w suffix n by 2. Here, the equation xk, instead of wn to the power 2, we can write as wn by 2 to the power kr for both the terms. So if we notice, the first term becomes n by 2 point DFT of the even samples of xk, and the second part is wn to the power k multiplied by n by 2 point DFT of the odd samples of xk. Now, if we represent the even samples of xk as xe of k, xk can be written as xe of k plus wn to the power k x odd of k, which is the sum of two n by 2 point DFTs. That means we have broken the n point DFT into two n by 2 point DFTs. Here, graphically, if we draw the diagram, we can see first we have divided x of n into the odd samples, that is x0, x2, even samples, that is x0, x2, x6, x4, x8, and the odd samples are x1, x3, x5 and x7. I find there is a problem in the even portion. Even portion would be 0, 2, 4, 6. Not 0, 2, 6, 8. It would be 0, 2, 4, 6. Because from 0 to 7 we have 8 samples. So there is a mistake in the even portion of xn. So now if we find n by 2 point DFTs of both the even and odd samples, we get x even 0, x even 1, x even 2, x even 3, and for the odd parts we have x odd 0, x odd 1, x odd 2, x odd 3, as we have derived in the last equation. Now, what we do, according to the last equation, we have to multiply the odd portions by wn to the power k and add the even and odd. Graphically, we show it by arrows. The upgoing arrows is for addition and the downcoming arrows are usually for subtraction. Now what we do is we multiply x even 0 plus w and w8 to the power 0 into x odd 0 to have x0 according to the previous equation. Similarly, we would have x1 would be xe1 plus w81 into x0 x odd 1. In this way, we draw the whole diagram. So further, if you keep on splitting the n by 2 DFTs into 2.n by 4 DFTs, we can remove the blocks by the cross sign, which is called the butterfly. That means in this diagram, if we move further, we break x0, x4 as the even part, and x2 and x0 and x4 as the even part, and x2 and x6 as the odd part, and again perform n by 4 point DFTs. Similarly, x1 for the odd part, x1 and x5 now becomes the even part, and x3 and s7 become the odd. So for x1 and x5 we again perform an n by 4 point DFT, and x3 x7 which becomes the odd part, we perform again n by 4 point DFT. In this way, if we move backward, we have these blocks replaced by cross signs, that is butterflies. So now what we are to do is only draw these diagrams, and one cross is called one butterfly. So here basically we are not at all performing any DFT. What we are doing is only multiplying with the Tweedle factor and then adding or subtracting. So if we move backward, as told earlier, that x0 and x4 will now be the even part, and x2 and x6 will become the odd part. So we divide into x0, x4. The sequence will be now x0, x4, x2, x6, x1, x5, x3, x7 as shown in this diagram. And the output will be capital X0, capital X1, capital X2. That is, here we see there is a bit reversal. If we denote 0 by 0, 0, 0, at the output you have, if you reverse 0, 0, 0, it would be again 0, 0, 0. But for 4, you have 1, 0, 0. If you reverse it, you will have 0, 0, 1. So at the output, you find capital X of 1. Similarly, small x of 2 is 0, 1, 0. If you reverse again, you have 0, 1, 0. So in this way, if you go on, we see the input and output has a bit reversal characteristics. So here basically we are just drawing the butterflies. We are just splitting the whole of FFT 8-point FFT into smaller portions, and if we proceed in this way, we find there is no DFT that we are doing. We are just drawing, and in the process we are adding and subtracting. So if something is left in this video, we will proceed with it in the next video, because the length of the video is getting a bit higher, and if some points are left in this video, I'll complete it in the next video.